Hi there. Hello. Today we're going to talk about probability again. We're going to talk about the multiplication rule. And we're going to start off by talking about independence. And two events are independent if when one event happens, it does not affect the other event in any manner at all as far as its probability goes. And just to kind of give you an idea what I mean by that, I want to practice this a little bit. So determine whether the two events are independent or dependent. So speeding on a freeway and being pulled over by the police. Well, those two things are definitely dependent. Meaning the one definitely could have caused the other and affected the other one. Whereas, number two over here, you have pancakes for breakfast and your best friend gets an A on her exam. These two events clearly have nothing to do with each other and are very independent. So let's move on and talk about the multiplication rule for independent events. So we're going to assume that these events are independent. And that brings us to the multiplication rule for independent events. So when events are independent, we basically multiply them together, exactly what the multiplication rule implies. And this has all sorts of real-life applications. This is very applicable. So here we're going to have a few scenarios, and one of them is that we have a company where two people work independently inspecting widgets. And their job is to identify the low-quality widgets. And what's the probability that an inspector does not identify a low-quality widget, which is going to be 20% or 0.2 probability. So the question becomes, what is the probability that both inspectors do not identify a low-quality widget? And what this would mean. So the probability that both miss a low quality. Well, the probability of one of them missing a low quality is 0.2. Using our multiplication rule here, we're now going to multiply that times the other inspector, which is also 0.2. And the cool kids would write 0.2 squared. So what we can do is go 0.2 raised to the second power. So once again, what is the probability that both will miss the widget? Well, there's about a 4% probability is what that means, that both would miss it. How many inspectors should be hired to keep the probability of not identifying a low-quality widget below 1%? Well, we could see two of them did not keep it below 1% because this is actually 4%, which is still too high. Let's try a third one. So that'd be 0.2 times 0.2 times 0.2. And once again, that's 0.2 to the third. Well, that actually is going to give us 0.008, which when we convert that to a percent becomes 0.8%, which is below 1%. So how many inspectors would that take? That would take a total of 3 inspectors. At least 3 inspectors. Now in real life, of course, not each inspector isn't exactly 20%, but you get the idea on how we're doing this. Let's do another scenario. What is the probability of obtaining 2 heads in a row when flipping a fair coin? Would it be unusual? Now, when we say unusual, we mean less than 5%. That's sort of a generic statistics amount. So unusual means less than 5%. So let's start. What's the probability of flipping 2 heads in a row? So the probability of 2 heads in a row, well, that's going to be, now the probability of flipping 1 head in the row, probability of heads, is 50%. And the probability of flipping and notice flipping the 2 are independent, meaning when I flip this first coin, it has absolutely no bearing on whether the second coin is going to have a heads or tails. It's still 50%. So 0.5 squared is 0.25. And this is not unusual, because it's not less than 5%, that's 25%. All right, separate from that, they want to know, separate coin, would flipping a coin 5 times in a row and getting a tails every time be unusual? 5 tails in a row. It sounds unusual, and it might be. Well, I'm going to use my notation here. 5 tails in a row, the probability of getting a tails for 1 flip is 50%. And how many flips am I doing? 5. So I'm going to go 0.5, here's my exponent button, raised to the 5th power. And here we get a number, 0.03125. Which I'd like to point out is 3.125%. Which is definitely less than 5%, making this unusual. So we're going to do a few more of these. This scenario says about 13% of the people of a population is left-handed. What is the probability that 3 randomly selected people are left-handed? Well, the probability, 3 lefties, is going to be the probability of left times the probability of left times the probability of left, which is going to be 0.13 3 times. So 0.13. And here's your exponent button right above here, the caret, raised to the 3rd power. That is going to give me about, actually exactly, 0.00217. Which again, if we interpret that, that is definitely less than 1%. That's 0.2197 of a percent. So very low probability of randomly selecting 3 left-handed people in a row. So we're back to a deck of cards, which has 52 cards in a deck. And 2 cards are randomly selected. What is the probability that the first card is a club and the second card is a club, if the sampling is done without replacement? So this is going to become a bigger deal, this with or without replacement. So without replacement, meaning a card is drawn and it's put aside. It's not put back in before the second one is drawn. Well, probability of a club and a club. Well, the probability of getting a club for the first one, how many clubs are there? There are 13 out of the 52. Now, once it's been removed and we didn't replace it back in there, now there's only 12 clubs out of 51. And you can see if we did a third, it would go down to 11 and 50 and so on. So I'm going to use my calculator. I'm going to put in parentheses 13 times 12 divided by parentheses 52 times 51. And that is going to give me about 0.058. Let's make that a little nicer. 0.588. Which is almost 6% chance of getting that. Now we're going to do the same thing, but we're going to do it with replacement. That means I draw a card, it's a club, and I put it back in the deck, and then draw again. Probability, again, of a club and a club. Well, that's going to be 13 over 52 twice, which is going to give about 0.0625. And you can see the difference in these numbers. With replacement or without replacement does matter. So when we replace it, it actually increases our probability of getting a second club. So due to a manufacturing error, 8 cans of regular soda are accidentally filled with diet soda and placed in a 24-pack. Suppose that the 2 cans are randomly selected from the 24-pack. We're assuming without replacement in this case. We're assuming someone is drinking these sodas. And to be clear, 8 of them are diet, which means that the remaining 16 regular. And this one wants to know what's the probability of getting a diet and a diet. Again, this will be without replacement. Well, again, that's the probability of diet times the probability of the remaining diets. That's going to be 8 over 24 times 7 over 23. And once again, I'm going to use my parentheses. 8 times 7 divided by 24 times 23. Which gives us 0.1014 about. So what's the probability of 2 of the cans being drawn, both being diet in this scenario? A little over 10%. And the probability that they're both regular, well, that's going to be there are 16 regular out of the 24. And once one is taken, that'll be 15 over 23. So once again, using my parentheses with my calculator, I get 4348. So in this scenario, what's the probability of getting both regular? A little over 43% chance. Next up, given 8 students, 3 of which are female, so 3 female, which gives us 5 male. If the 2 students are selected at random without replacement, meaning once one's taken, then the whole group has dropped down, what is the probability that both students are female? So probability, both female. Well, how many females are there? There's only 3 out of the 8. And she's not replaced back into there, so that makes it 2 out of 7. Once again, make sure you use your parentheses on when you're dividing these out. It would be really easy to mix something up. And that's going to be 0.1071. Now, I'm expecting you to use your calculator for every single one of these to verify all of these numbers. And I'm going to leave that last one there and move on to this next part. Computing at least. Often when we say at least, we're going to use the complement rule. We've used the complement rule before. This is like 100% minus the amount. A good example that I use in my classes are if 60% of the people in my classroom are male, then 100% minus 60% is 40% are female. All right, we are here. So among 30 to 35-year-olds, 38% say that they have danced in public while under the influence of alcohol. Suppose 5 30 to 35-year-olds are selected at random. Here I've listed out, it's possible none of them, of these 5, have danced in public under the influence. Maybe only 1 of the 5 have, 2 of the 5, 3 of the 5, 4 of the 5, and possibly all 5 of the 5. That seems unlikely, which we will see here in a second. So to be clear, probability that they've danced in public under the influence is 0.38. Probably not danced is I'm going to use the complement 1 minus 0.38, which is 0.62. Here we have, what is the probability that none of them have danced in public while under the influence of alcohol? Probability that none, well, that's going to be that all of them, 0.62 times 0.62 times 0.62, how many times? 5 times. Let's see what that becomes. So a little over 9% chance that none of them have ever danced in public. And this brings us to our at least scenario. So what is the probability that at least one has danced under the influence of alcohol? Well, this is going to be a lot easier. To do at least one means I have to figure out the probability of one of them did plus probability of two of them did. And there's other complications that are involved. So the easiest thing to do, so at least one is the same as 1 minus the probability of none, which we calculated up here. So it's just a complement. Minus 0.0916. And using my calculator, I get about 0.9084. So, which makes sense. There's more than a 90% chance that at least one, maybe 2 or 3 or 4 or all 5 did this. And what is the probability that all 5 have danced in public under the influence of alcohol? Well, that's going to be 0.38 raised to the 5th power. And that's going to be pretty darn low. Which again makes sense since each one only has a 38% chance of falling into this category. All right. Here we have a Christmas light scenario. Christmas lights are often designed in a series circuit. This means that when one light burns out, the entire string of lights go black. Suppose that the lights are designed so that the probability a bulb will last 2 years is 0.995. So probability 2 years, 0.995. The success or failure, there's an or, of a bulb is independent to the success or failure of the other bulbs, meaning they're independent of one another. What is the probability that a string of 100 lights where all 100 will last 2 years? Well, all 100 lasts 2 years. Well, that's going to be 0.995 to the 100th power. Because each one has its own probability of lasting 2 years of 0.995, and there's 100 of them. So 0.995 times 0.995 times 0.995 and so on. Well, using my calculator, 0.995 raised to the 100th power. You can see that drops down pretty big. It's about 0.6058. Once again, I want you verifying all these and practicing with your calculator. So, probability of them lasting all 100 of them lasting 2 years, pretty low, not all that high. What's the probability that at least one will burn out? Well, probability that more than one will burn out? Well, that's going to be the same thing as saying 1 minus the probability that none of them burn out. Which again is what we just figured out here. So that's going to be 1 minus 0.6058, which is approximately, I'm going to go here, 1 minus 0.6058 is about 0.3942. All right. Move to the last page of this section. Here we have conditional probability. So we have new notation here. This is pronounced the probability of event F happening given that event E is going to happen or already has happened. And here's how we interpret this. We can use it with probabilities or we can use it with numbers. It ends up that the denominators cancel out here to get this. And here's an alternative way of writing that. So let's start here. So we're back to a deck of cards. Suppose that a single card is selected from a standard 52 card deck. What is the probability that the card drawn is a queen? Okay. How many queens are there? There are 4 queens, one of each suit out of the 52. And that comes out to be 1 over 13. We'll just leave it in fractions for now. Now suppose that a single card is drawn, but it is told that the card is a court meaning face card. Courts is how they say it in England. So this is saying the probability of a queen being drawn given that we're only taking from face cards. Well, how many queens are there? There's 4. How many face cards are there? There's 12. So we have a 1 in 3 chance of drawing a queen given that we're only drawing from face cards, which makes sense. The queens make up 1/3 of the cards. And to be clear, this became the probability of, let me write it over here, the probability of a queen and a face card divided by the probability of face cards, or number. So here we go. So here's that same survey that we had before. And this is whether the freshman, sophomore, junior, or seniors are satisfied with their student government or not. And we're going to say, what is the probability that he or she is not satisfied with student government? So probability not satisfied with the student government. Here's the not satisfied. There are 76 over the 371. 76 divided by 371. It's about, it says to round it off to 3 decimal places there. 0.205. Okay. So given that the participant is a junior, what's the probability that he or she is not satisfied? Okay, so this is the probability of not satisfied given that they're a junior. Well, this is going to be the probability of not satisfied juniors divided by the probability that they're juniors. Well, if we look here, the probability, or the number, I guess, of not satisfied juniors. So here are the juniors, and how many of them are not satisfied? There's only 12. What's the probability that they're junior? Well, how many juniors are there? 89. And this makes sense. Suppose we know that a participant is satisfied. What is the probability that he or she is a senior? So this is kind of flipped around. Probability that they're a senior, given that they are satisfied with the student government. So this is the probability of satisfied seniors divided by the probability of satisfied students. And I'm using the number count, not the probability, obviously. So how many satisfied seniors are there? Here's seniors. Satisfied is 62. Satisfied total, 236. Once again, 62 divided by 236.